In this video, I'll show you how to use the logic of hypothesis testing. Inferential statistics is the practice of making an inference about a population parameter, usually a percentage or a mean, based on a statistic in a sample. And we do this by simulating many repetitions of the survey or study. Let's look at an example. Suppose you flip a coin 20 times, and it seems to land on heads a lot. In particular, it lands on heads in 12 out of the 20 flips. So you're wondering what the overall likelihood is of the coin landing on heads. We're interested in all possible flips of the coin. This is the population. And we need to specify the variable and parameter to make a model for the population. In this case, the variable is the face that lands up, heads or tails. The parameter is the percent of all possible flips of this coin that land on heads. Then comes the most important step. We need to make a hypothesis about the value of the parameter. We could hypothesize that the coin is fair and that 50% of all flips would land on heads. Or we could hypothesize that 25% of all flips would land on heads, or 40%, or any other percentage. We can make any hypothesis we want. For this example, let's hypothesize that 40% of all flips would land on heads. We start by building a model where 40% of the flips are heads, and we'll flip 20 coins in each set. And each time we repeat the sample, we get a different percentage of flips that are heads. And after having simulated 1,000 sets of 20 flips, let's look at a distribution of the results. Here is a histogram of the distribution of the percent of heads in each 20-flip trial. Now, each item in this distribution is one trial of 20 flips. The particular trial I've highlighted is one trial where 45% of the flips were heads. And what is particularly important is that this is all made by assuming 40% of all flips of this coin will land on heads. And that is so important that I'll add it to the top of the histogram. To help us think about what this sampling distribution is telling us, let's add some counts to the bars. So this bar in the middle corresponds to 180 out of the 1,000th trials of flips. That's 18%. So it's showing us that 18% of the trials had 40% heads. And the key is that this is assuming that 40% of all flips would come up heads. Now, you might be thinking, if we're assuming that 40% of all flips are heads, why don't all of the trials have 40% heads? Well, that's due to sampling variation, and the fact that each trial only consists of 20 flips. And looking at this histogram, we can see that it wouldn't be that surprising to get a trial with between 35 and 45% heads. In particular, 50.6% of trials had 35% to 45% heads, assuming that 40% of all flips are heads. So it wouldn't be particularly surprising to get between 35% and 45% heads in a trial of 20 flips of a coin that is going to land on heads in 40% of all of its flips. And if we include some additional outcomes, 74.7% of trials had 30% to 50% heads, assuming that 40% of all flips are heads. So it wouldn't be particularly surprising to get between 30% and 50% heads in a trial of 20 flips of a coin that lands on heads in 40% of all flips. And if we include some additional outcomes, 89.3% of trials had 25% to 55% heads, assuming that 40% of all flips are heads. Now, let's think about the outcomes that we haven't yet included. Our hypothesized parameter value was 40%, and the observed statistic was 60%. This is a difference of 20 percentage points. So we're also looking at the outcomes that are 20 percentage points below the hypothesized parameter value. And in this range, only 10.7% of the trials had 20% or less, or 60% or more heads, assuming that 40% of all flips are heads. Now, our coin landed on heads on 60% of its 20 flips. So, this 10.7% is the probability of getting our observed statistic, or one further from the hypothesized parameter, assuming that 40% of all flips are heads. This probability is called a p-value. And if our coin was one that lands on heads in 40% of all of its flips, it would be a little surprising if we flipped it 20 times and got 60% heads. Specifically, if 40% of all flips are heads, having the coin land on heads in 60% of 20 flips would be among the 10.7% most surprising outcomes. But this is exactly what we observed, that 10.7% is the probability value. Since what we observed would be relatively surprising, then this is moderate evidence against the assumption that 40% of all flips are heads. And now, what if instead of 60% heads in 20 flips, we had gotten 65% heads? Then, if 40% of all flips are heads, having the coin land on heads in 65% of 20 flips would be among the 3.6% most surprising outcomes. Now, the p-value is 3.6%, and this low probability is stronger evidence against the assumption that 40% of all flips are heads. It doesn't prove that the assumption is incorrect, but it's stronger evidence because if the assumption was correct, then the observed result would be more surprising. Now, let's summarize what we've seen here. What we did was to test a hypothesis. Specifically, we first made an assumption or hypothesis about the value of the parameter. In our case, we assumed that 40% of all flips of the coin would be heads. Then we created a model to match the assumption. In our case, the model had 4 heads and 6 tails. Then we simulated repeating the study. In our case, we used 1,000 trials of 20 flips each. Then we constructed a sampling distribution from the simulated trials, and we compared the observed statistic of 60% to see how likely it would be to get such a statistic. This probability we computed is called a p-value, and if there was a low probability of getting our observed statistic, then this was evidence against the assumption.